Okay, moving on to start talking about our second section of the lecture today, which is about the constituents of the Earth's atmosphere. Before we get any farther in that, let me just make sure that you understand what this word constituents means. This is this word constituents in terms of like ingredients, what it takes to make up, in this case, the atmosphere. And, you know, I mean, again, it's the first day of a class, we have to have our kind of cheesy definitions here, and one of the definitions that we need to have is, what is air? And I like this definition that came from the textbook about air is a mixture of gases and aerosols. Let's forget about this word aerosols for a minute and focus on this word mixture. I mean, I think you guys know what gases are, right? You got to this point in your education, you know what gases are. Mixture, as in they've been stirred together and they are combined, but they're still separate. They're separate materials. Think about Kool-Aid. When you make Kool-Aid, you pour water together with sugar and the flavoring packet that comes when you make Kool-Aid, and store it together. It is a mixture. But I mean, it's still made of water molecules and sugar molecules and whatever the molecules are that are in the Kool-Aid packet. They're not changed, they're just cut together. And that's the same with the atmosphere as well. We're going to find out that it is a mixture of gases, things like nitrogen and oxygen and carbon dioxide and water vapor. And they're mixed together, but they're still separate. I mean, there's still oxygen molecules and carbon dioxide molecules and so on. We'll come back to this idea about aerosols in a little bit, because that's a whole different thing. But think about all these gases that are out here in the air with us. There's gases like nitrogen and oxygen and water vapor and carbon dioxide. All these gases got here somehow. Somehow or other, these oxygen molecules got into the atmosphere, and the process by which they are added to the atmosphere is called a source. That's in contrast to a process that removes them from the atmosphere that's called a sink. Now, before we get any farther, let me just give you a little, let me let you in on a little secret, if you will. Behind the scenes on a course like this, we actually have a set of goals as to what the students are going to learn over the course of the semester. And then over the course of the semester, there are special questions on the test that measure, did you actually learn that? No one tells us we are or are not supposed to tell you about those goals and so on, so I'm going to tell you about one of them right now. One of the important goals in this course is understanding about sources and sinks. Processes that add something to the atmosphere, a source, or a process that removes something from the atmosphere, called a sink. Now, we're going to be talking about sources and sinks today in terms of like gases. What is a source of oxygen? What is a source of nitrogen? What is a sink of carbon dioxide? But we'll actually see these terms over and over again over the course of the semester. They will be on the test. They will be on the homework. You are being measured in terms of how well you are being assessed as to how well you understand these terms. So let's make sure we get them. Let me focus first of all. Let's look at that word source. All right, if we were talking about like water vapor, what is it? Water vapor is a gas in the air around us. We would probably use the word humidity to describe it. What is a source of humidity in the atmosphere or water vapor in the atmosphere? Well, the source of it, the process that adds that gas to the atmosphere, would be evaporation. If there were water on the ground right now, as it is added to the atmosphere, that would be a source of water vapor to the atmosphere by the process of evaporation. Probably better would be the use of the word evapotranspiration. Evapotranspiration includes the effects of how plant leaves add water vapor to the atmosphere as water vapor escapes through the leaves of the plant. In contrast, a sink for water vapor, if we were talking about how we remove water vapor from the Earth's atmosphere, I'd go with condensation, where we are changing water vapor back into liquid water droplets. That could be like the formation of dew overnight, as you condense water vapor in the atmosphere out into little drops of water on the grass. Or that could be the formation of a cloud. Clouds are made up, as we're going to learn in this class, of tiny little droplets of water. They're liquid. Water vapor is condensed into cloud droplets in the cloud. And so, okay, we've got this idea of a process that could add water vapor to the atmosphere, or processes that could remove it, a source of water vapor, or a sink of water vapor. Watch for those ideas not only through this lecture, but really all semester, okay? I guarantee that kind of stuff is on the test. Now, each of these gases that we have up in the atmosphere is going to have two important properties associated with it that describe how that gas gets in the atmosphere and stays in there. There's going to be two key terms here. One of those terms is the reservoir. The reservoir, when you think about reservoir in the context of like a lake, right? A lake, when the Corps of Engineers builds a reservoir, it's an artificial lake that stores water. The word reservoir means like as in it's how much is being held. A good dictionary definition of reservoir in this context then would be the amount of the gas that's currently in the atmosphere. Now, this could be measured in terms like kilograms. How many kilograms of oxygen are in the atmosphere? It's going to be a big number. Or it could be like a density, or it could be parts per million or something like that. But it's just a way of measuring. When we talk about the reservoir of a gas, then we're talking about like how much of it is there out there in the atmosphere. You know, typically expressed in something like kilograms or something like that. Then, because we have this idea of reservoir, we also have ideas like sources and sinks. Gases get added into the atmosphere, they're part of the reservoir of that gas, and then they eventually are removed from the atmosphere by a sink process. How long were they up there in the atmosphere? The residence time. The average amount of time, or a typical amount of time, a given molecule of that gas will actually spend up there in the atmosphere. That will have units of time, something like seconds or years or something like that. So for example, for oxygen, a source of oxygen for the Earth's atmosphere is photosynthesis. The plants are putting oxygen into the atmosphere. The oxygen enters the atmosphere and becomes, you know, a part of the reservoir of that gas in the atmosphere. But at some point, we breathe it in and take it out of the atmosphere as it enters our bloodstream through the process of respiration. Respiration is a sink of oxygen in the Earth's atmosphere. And therefore, there was a certain amount of time that a typical oxygen molecule got to be loose up there in the Earth's atmosphere. That's its residence time. There's actually going to be a formula for computing this. Some gases are going to have very long residence times, like millions of years, and some gases are going to have relatively short residence times, like days, okay? And some will have it someplace in between. This is something that we need to be able to compute about the atmosphere. And so we're going to use this little formula where the residence time of a gas is just the reservoir of the gas, which is going to have units of something like kilograms, divided by the input rate. How fast we're adding that gas to the atmosphere. So like the input rate might be something like kilograms per second. Okay, how many kilograms of oxygen are being added to the atmosphere every second by photosynthesis in plants? And you're dividing that number into the reservoir. How many kilograms of oxygen are there out there? So this is going to have, you know, the numerator is going to have units of like kilograms, the denominator is going to have units of like kilograms per second, and if you work out those units, it works out to, in this case, to be seconds. Okay. Once you have them in units like seconds or whatever, you could convert them to years or whatever it needs to be if you have like a giant number of seconds. So let's start thinking then about these individual gases. Let's take some examples of some individual gases and think out what would their residence time be. For example, let's consider the example of water vapor. Now, the reservoir of water vapor is actually relatively small. We're going to see in a little bit that, you know, only under the very most humid conditions is the amount of water vapor in the Earth's atmosphere even as much as like 1% of the air. Okay? Compared to other gases in the Earth's atmosphere, there really isn't that much water vapor. So the reservoir of water vapor is pretty small. So the numerator of our equation there for residence time, the numerator, the top, is the smallish number. I mean, don't get me wrong, it's still going to be millions and millions of tons of water vapor, but it is small compared to when we get to like nitrogen or something like that. Now, the input rate, on the other hand, is relatively fast. You know, 70% of the Earth's surface is covered by the oceans. All those places have evaporation going on all the time. Most of the rest of the surface of the Earth is covered with plants. They're continually pumping water vapor into the Earth's atmosphere by the process of evapotranspiration. There's actually a lot of processes that are adding water vapor to the Earth's atmosphere. The input rate is pretty fast. So the denominator, the bottom of the fraction there, is going to be a pretty big number. So you have a relatively small number in the numerator divided by a relatively big number, you end up with a relatively short residence time for water vapor. In fact, if you work through the math, it works out to about 10 days. In other words, someplace out over the ocean, a water vapor molecule, you know, evaporates off the ocean and is now part of the atmosphere. On average, it will take about 10 days before that condenses out and is once again a liquid, you know, that falls out in the form of rain. All these plants around me right now are evapotranspirating water. Their roots are pulling water out of the soil and putting it up into the atmosphere through the process of evapotranspiration. Those water vapor molecules will on average be up there in the atmosphere for about 10 days. That's a relatively short residence time as gases go. On the other hand, let's consider the example of oxygen. Now, oxygen is another gas in the Earth's atmosphere. This gas has a relatively a relatively large reservoir. We're going to see in a little bit that about 21% of the Earth's atmosphere is oxygen. That's a lot of tons. I mean, that's billions and billions of tons of oxygen out there in the Earth's atmosphere. Now, the input, so the numerator of our fraction there, when we're doing reservoir divided by input rate, the numerator is fairly big, but the input rate is pretty big too. The rate at which oxygen is being added to the Earth's atmosphere by photosynthesis in plants is pretty fast. So the denominator of that fraction is pretty big too. So you have a big number in the numerator, but a biggish number in the denominator as well. When you actually work out the math, you end up with a fairly, let's say, moderate residence time. A typical estimate is somewhere around 500 years. So right now, these plants around me are putting oxygen into the atmosphere by the process of photosynthesis. And as they do that, those oxygen molecules are liberated and they're flying around in the Earth's atmosphere. They're a constituent of the Earth's atmosphere. At some point, they'll be breathed in. Now, actually, every time you breathe in, the vast majority of the oxygen molecules actually get breathed right back out. Your lungs are not that efficient at moving oxygen across into your bloodstream. But at some point, you will breathe those oxygen molecules in, and they will be taken out of the atmosphere and put into your bloodstream. They'll have been removed from the atmosphere by the process of respiration. That is, the sink of the oxygen will have been respiration. And the average amount of time that those oxygen molecules will have been bumping around in the Earth's atmosphere is about 500 years. That's a lot longer than 10 days. Now for the one more example, let's do nitrogen. Okay, nitrogen, N2, two nitrogen atoms hooked together to make a nitrogen molecule. Nitrogen is by far the biggest constituent of the Earth's atmosphere. It's like 78% of the Earth's atmosphere. The reservoir of nitrogen is huge. On the other hand, the input rate of nitrogen to the Earth's atmosphere is really, really slow. The processes that add nitrogen to the Earth's atmosphere, the sources of nitrogen in the Earth's atmosphere, are not that fast. They're like processes that bacteria engage in soil. Okay? The input rate is a very small number. So you have a huge number in the numerator for residence time. You have a small number down there in the denominator for the input rate. You end up with a very, very long residence time. If you actually work through the math, you end up with 42 million years. In other words, right now, maybe in the soil around me, there's some nitrogen-fixing bacteria that are doing some things, and they are adding or removing nitrogen from the Earth's atmosphere. Those nitrogen molecules are going to be bouncing around in the Earth's atmosphere for about 42 million years before the sink of nitrogen removes them. And the sink of nitrogen is also certain processes that bacteria do in the soil. 42 million years is a lot longer than 500 years for oxygen, and it's a lot longer than 10 days for water vapor. In fact, this gives us an idea that actually, based on the residence time, we should be able to sort the components of the atmosphere, or the constituents of the atmosphere, out into two piles. We're going to say that depending on their residence time, we're going to call them either constant constituents of the Earth's atmosphere, or we're going to call them variable constituents of the Earth's atmosphere. Let's start with the constant constituents. Constant constituents are gases that are in the Earth's atmosphere that occur at about the same concentration anywhere you go in the atmosphere, whether from one location to another, or one height to another, or from one time to another. Good examples of the constant constituents that we've seen so far have been nitrogen and oxygen. Oxygen is about 21% of the Earth's atmosphere. It's 21% of the Earth's atmosphere right here where I'm standing. It's 21% of the Earth's atmosphere where you're standing. If I went up in a hot air balloon, it's 21% of the Earth's atmosphere up there. Now don't get me wrong, the total amount of air up there is going to be less. There might not be all that much oxygen up there, but it's because there isn't that much air. Okay? Everywhere we go, it's about 21%. Why? Because 500 years is a really long time. Once that oxygen is added to the Earth's atmosphere by, say, a forest, for 500 years, the winds and the storms and the circulation of the Earth's atmosphere stirs the Earth's atmosphere. There isn't more oxygen over here by this tree than there is over by that field, than there is over that parking space over there, because over the course of time, it all gets stirred together. Imagine, for example, if you were making a cake, okay? If you first pour all the ingredients into the big bowl. You've got cake mix and eggs and milk or whatever's all in cake. I have no idea. If you kind of just stirred it a little bit, there'd still be places in that bowl where there's more flour and less egg, and over here there's more egg and less flour, and it wouldn't be very well mixed. You could go from one place to another in the bowl, and you'd have different amounts of each of the constituents of the cake mix. On the other hand, if I stirred that cake mix for 500 years, there would be exactly the same amount of egg as cake mix, as oil, as water, whatever is all in cake, in every single spot. And that's the way our atmosphere works too. 500 years is a really long time. By that time, over that period of time, all the oxygen is all just evenly mixed throughout the Earth's atmosphere. Same with nitrogen. Nitrogen is going to be a constant constituent too. 42 million years? 42 million years of mixing. It isn't like the air farther away from the background. I mean, if the soil is where the nitrogen comes from the bacteria that are in there, it isn't like there's going to be more nitrogen near the ground. For 42 million years, that's all being stirred together. In contrast, we're going to have the variable constituents. These are going to be gases that have relatively short periods of time that they last in the Earth's atmosphere. There'll be more of those gases near their source. There'll be less of those gases near their sink because they haven't had time to be evenly mixed. Water vapor is going to be our greatest example of this because, like, you know, there's a wide range of where water vapor can come from on the Earth's atmosphere. Over the ocean, there's huge sources of water vapor. We can be adding water vapor all the time. Over deserts, there's almost no water vapor being added. And 10 days is not enough time for the winds to stir the water vapor, to spread the water vapor evenly over the whole planet. Long before the water vapor would be stirred evenly where every place on the Earth's atmosphere had the same amount of water vapor, the water vapor will have condensed out in the form of clouds and precipitation or dew or something like that. We'll be learning more about that in the lectures to come. But this idea that we're going to be breaking the list of gases up in the atmosphere up into constant constituents, the ones that it doesn't matter where you go, they're the same amount, and variable constituents, which you have to measure because there could be a very different amount in one place versus another, will be interesting. Let's focus first on the constant constituents. We would say that the constant constituents of the Earth's atmosphere, here's a power vocabulary word for you, we would say that they're in steady state. When we say that they're in steady state, what we mean is the input rate of that gas is about the same as the output rate. We're not getting more and more oxygen all the time in the Earth's atmosphere. The addition of oxygen to the Earth's atmosphere by photosynthesis is almost exactly the same as the removal of oxygen by the sink process, which is respiration. And so they're in basically steady state. The amount of oxygen doesn't change from time to time. 500 years is more than enough time for it to be well mixed through the Earth's atmosphere. It doesn't change from place to place, etc. Usually there's actually some kind of equilibrium going on between the sources and sinks, but we won't get too bogged down in that. You might notice there's a paragraph or two about that in your book. If I made a little pie graph here to show you your constant constituents of the Earth's atmosphere, what you'd immediately notice is nitrogen just runs the whole show. 78% of the Earth's atmosphere is nitrogen. 21% is oxygen. 78 plus 21 is 99%. 99% of the Earth's atmosphere is just nitrogen and oxygen. Yeah, absolutely. And another gas, argon, it's only 0.9%. So now let's see, we got 99.9% of the Earth's atmosphere. We've only looked at 3 gases. Yep, those 3 gases are pretty much the whole show. We know nitrogen is actually not that interesting in terms of what it can do. Nitrogen is very inert. It kind of just takes up space in the atmosphere. Oxygen, of course, is very interesting in terms of its role for life and so on. Argon, again, isn't very reactive, and neither is our 4th gas on there, neon. Neon being so small. By the way, that is the order. Those are the 4 biggest gases in the Earth's atmosphere in terms of how much of the Earth's atmosphere they occupy. You don't have to know these numbers, by the way, although the first 2 might be kind of handy to keep, have a broad sense that about 3/4 of the Earth's atmosphere is nitrogen and about 1/4 is oxygen. It's more likely that you'd have to do something like put these constituents of the Earth's atmosphere in order from most abundant to least abundant or something like that. In contrast, the variable constituents of the Earth's atmosphere have concentrations that vary from place to place or from height to height or from time to time. You need to measure them. Because they're not going, I don't need to measure how much oxygen's out there. When a meteorologist goes out to take a weather observation, they don't measure how much oxygen there is. We know it's going to be 21%. okay? But we do have to measure the amount of water vapor in the Earth's atmosphere, the humidity, because it's going to vary a great deal. So, for example, water vapor. Water vapor can range from basically 0% of the Earth's atmosphere under very dry conditions to, okay, your textbook says 4%. That would be ridiculously humid. I mean, I suppose it's physically possible. A good average worldwide would be something like 1/4%. Not very much of the Earth's atmosphere is water vapor at any given time. Hey, I like that little picture, by the way. I included on there. That is a special type of satellite image called a water vapor satellite image. When you think of satellite pictures, you're thinking of, like, you know, there's cameras on the satellite and looking down and it shows you things you can see. There are other types of instruments on a satellite as well that can measure other things, and one of the things they can measure is the humidity of the air. And so what you're basically seeing there is a satellite picture that showed the humidity of the Earth's atmosphere at a particular day, with white being more humid and browns and blacks, or whatever the color turns out to be, being less humid. And you can see that there are places that are very humid and there are places that are very dry, and you know, you need to measure the amount of water vapor in the Earth's atmosphere in order to know how much it's going to be. Another variable constituent of the Earth's atmosphere is carbon dioxide, or CO2. Recently, the carbon dioxide concentrations in the Earth's atmosphere hit 400 parts per million. You know, part of the story is that carbon dioxide is increasing with respect to time. If we zoom in here, you can see how there's kind of a trend. These are carbon dioxide measurements that come from a particular weather station that's famous in Hawaii, far from any sources of pollution or anything like that. You can see how there's an upward trend over the last, few decades. I don't know how long the particular graph that I have here extends, but you can see that there's this upward trend in the amount of carbon dioxide in the Earth's atmosphere, and that's due to the burning of fossil fuels. Gasoline, diesel, coal, things like that, natural gas, etc. Adding those gases to the Earth's atmosphere has increased carbon dioxide from a pre-industrial level of about 280 parts per million, roughly, to now we have crossed 400 parts per million. So we haven't quite yet doubled the amount of carbon dioxide in the Earth's atmosphere, but we're getting there. By the way, you can see how there's also kind of a little wiggle to the line. There's sort of an annual cycle to the amount of carbon dioxide in the Earth's atmosphere. That has to do with the fact that carbon dioxide's removed by plants, right? Plants are the sink of carbon dioxide. They remove carbon dioxide as part of the process of photosynthesis. The source of carbon dioxide, of course, being respiration. Well, there are different amounts of plants in the northern hemisphere and the southern hemisphere. The northern hemisphere has much more land than the southern hemisphere does, and a lot of the land in the southern hemisphere is Antarctica, and Antarctica doesn't have any plants. So in northern hemisphere summer, when plants are active, they're removing a lot of carbon dioxide from the Earth's atmosphere, and the total amount of carbon dioxide in the Earth's atmosphere goes down. In the winter, in the northern hemisphere winter, when plants are dormant in the northern hemisphere, they're not removing carbon dioxide from the Earth's atmosphere, and the total amount of carbon dioxide goes up for a while. So there's this really neat annual cycle to the amount of carbon dioxide in the Earth's atmosphere, just due to the fact that there's so many more plants in the northern hemisphere than the southern hemisphere. But then none of that is enough to counteract the fact that we are rapidly adding carbon dioxide to the Earth's atmosphere, and we'll be learning this semester about the consequences of that. Another good example of a variable constituent of the Earth's atmosphere is ozone. Ozone is a gas. I know sometimes you hear about the ozone layer or the ozone hole. That can be confusing because you don't get the idea from that ozone is actually a gas. I mean, we could fill a balloon with ozone, or we could fill a jar with ozone or something like that. It's a nasty, toxic gas, but it's also necessary for life on Earth, as you're going to see in a later lecture. And it's a variable constituent. You have to measure the amount of ozone there is in any given location. That's how we found the ozone hole. Again, we're going to have a whole lecture about the ozone hole and so on coming up. But the ozone hole is this area over the southern hemisphere where the ozone concentrations have basically fallen to zero. On this other diagram here, I want to show you, this is the profile of the amount of ozone at different heights in the Earth's atmosphere. And what I want you to notice is, boy, there's that big spike in the amount of ozone, about 25 kilometers above the Earth's surface. That's the ozone layer. It's a place in the atmosphere where there's a lot of ozone. We'll learn more about why and what it's good for and all that kind of stuff. But see, again, here we had to actually measure. You can see how at different heights there was a very different amount of ozone at different heights above the ground. We'll learn about the sources and sinks of ozone. Not the next lecture, I don't think. Well, maybe it's the next lecture. It's either the next one or the one after that. Another variable constituent of the Earth's atmosphere is methane. Methane is natural gas. It is what is, if you have a gas stove or gas heat in your home or whatever. But that kind of natural gas comes from wells. They mine it, they frack it out of the ground and so on. Um, in the atmosphere, part of the increase in methane in recent years has been because, like, you know, the pipes that distribute natural gas are very leaky, as are the wells. But most of the increase is actually because two important sources of well, actually several important sources of methane have been increasing. One is cattle, particularly cattle in high-density feed yards. There's no easy way around it. Cattle flatulence, cow farts. Cattle that are raised in high-density feed yards, they have a lot of gastric trouble, and they produce a lot of methane gas by farts, and this gets added to the Earth's atmosphere. It's an important source of methane. Another source of methane is termites. Termites are perfectly natural, but there are increasing numbers of termites in the Earth's in the ecosystem. It's beyond the scope of the class-wide number. Termites are increasing, but they produce methane as well. Also, rice paddies. You know, like where they grow rice in those flooded fields. They look beautiful, but rice paddies are actually environmentally a disaster, and the bacteria that live in rice paddies produce a lot of methane. So you can see again the amount of methane in the Earth's atmosphere has been increasing dramatically over the last 100 years or whatever it is. All right, if we go back and start talking back to our original definition of what we meant by air. We said air is a mixture of these gases. They might be variable, they might be constituent gases, and aerosols. Let's time to talk about that word aerosols for a minute here. Aerosol are any kind of little particles of solid or liquid that are suspended in the Earth's atmosphere. This can be things like soot, smoke, dust, pollen, salt, etc. Things, little specks that are in the Earth's atmosphere. They're way too small to see. Okay? The air is full of this stuff. There are hundreds of thousands of them in every cubic centimeter of the Earth's atmosphere. And there's a few hundred of them in every cubic centimeter of the Earth's atmosphere that are surprisingly big. I mean, they're still too small to see with the naked eye, but they are big enough that they are involved in the processes, for example, as to how clouds get made and so on. But we'll learn all about that in a coming module of the course. Soot, smoke, pollen, dust. My guess is you don't have terrible difficulties figuring out where those kind of things would be coming from. Salt might be kind of a mysterious one for you. There's a lot of salt in the Earth's atmosphere. In fact, salt can be the biggest, in terms of how much of the aerosol there is, salt can be the biggest one. Salt comes from the ocean. When salt water, when there's a splash of a wave, it produces these little droplets of sea spray, and some of those sea spray droplets will evaporate before they hit back into the ocean. There's salt water, the water evaporates off, and it leaves behind a little crystal of salt in the atmosphere. Salt crystals are going to turn out to be very important for like the formation of raindrops and so on, but again, we'll get to that in a later module.